It's my pleasure to introduce today's speaker, Matt Novack. Before his talk, maybe I'll just say a few words. Matt received his PhD from UT Austin under Alex Vassal in 2019, and after that he was Quran instructor till 2021. And this current year, he's a postdoc in the IIS, and he will join Purdue in the fall. So today his talk is title is Intermittent Onsager Theorem. Okay, Matt.
All right, thank you, Chang Yu, for the invitation and the introduction, and thanks to all the organizers. So the subject of my talk today is of recent joint work with Vlad Vicol at NYU that appeared on the archive a few months ago. And that work is itself based on another joint work from a little more than a year ago with Tristan Buckmaster, who's my colleague at the IIS this year, and then also Nader Masmoudi and Vlad. And this is a talk about fluid equations. This theorem, I've called it an intermittent Onsager theorem. And my goal is to convince you that it has something interesting to say about turbulent fluids. And so let me write down the PDEs that we use to describe these fluids. So these are the Navier-Stokes and Euler equations. And throughout this talk, the unknown velocity field will always be a function of time and space, where the spatial variable belongs to the three-dimensional torus. And for the sake of generality, I've allowed some body forcing term, and the pressure appears in the equations as well. And these equations represent the balance of momentum. That's the first equation, and the conservation of mass, which is the incompressibility constraint encompassed by this div u equals 0. And there's a parameter appearing in these equations, which is the kinematic viscosity coefficient nu. And the Euler equations correspond to the case that nu equals 0, so we lose this term, and Navier-Stokes is when nu is positive. And scientists, mathematicians, computational fluid dynamicists, physicists, we use these equations to describe turbulent fluids. And turbulent fluids arise when the value of this kinematic viscosity coefficient is very small. And turbulence is something that we can observe, first of all, in experiments, either in the lab or out in the world. And we can make measurements of turbulent fluids and intuit or derive what I'll refer to as experimental facts. And I'll give as precise a meaning as I can to these experimental facts later. The first two, if you ask any physicist, they'll tell you exactly what is meant by these. The third one is a little bit harder to pin down, but that's of course one of the main points of my talk. And in addition to observing these properties of turbulent fluids in the lab in experiments, one can also simulate the PDEs on a computer. And if you simulate the Navier-Stokes equations on a computer, you can check whether or not these properties are exhibited in your simulation. And to a remarkable degree, the experiments and the simulations really match. And so this tells us that the PDEs themselves are really capturing at least a good portion of the fundamental physics which is at play here. And so then that leads me to sort of the motivating question for my talk, and also more broadly for what could be called the Onsager program, which has attracted a lot of attention in my community recently. And so the motivating question then is this: given that both experiments and simulations are telling me certain things about turbulent fluids, I want to know at a mathematical level if the solution theory to the PDEs is consistent with those observations. And in today's talk, that will mean building dissipative intermittent solutions to the Euler equations. So roughly speaking, that's the goal of this work. All right, so let me say a few simple things about the Euler equations before I give a rough statement of our theorem. All right, so we saw the unknowns, the velocity u, the pressure p. The pressure can in fact be recovered by solving this elliptic equation. So if you like, the only unknown is really the velocity field u. And the natural conserved quantity, or one of them at least, is the energy. And I can deduce this conservation law by taking the dot product of the equation with u and integrating by parts. And at least for smooth solutions, I deduce that this quantity is constant in time. All right, but I will not be considering smooth solutions in this talk. And there's two good reasons for considering weak solutions. And those are, one is mathematical and one is physical. And at a mathematical level, I should care about weak solutions because it is expected that even from smooth initial data, the Euler equations dynamically produce singularities. And in order to study solutions with singularities, I need weak solutions. All right, at a physical level, as we'll see, turbulent flows are dissipative, meaning that this quantity is in fact not constant in time. And since smooth solutions have this quantity as a conserved quantity, it must be the case that the physically relevant solutions are not in fact smooth. They must be weak solutions. All right, so the theorem in a rough sense can be stated as follows. So there exist solutions to 3D Euler posed on the periodic box for which the energy is decreasing. That's the dissipativity. And these solutions have a property which I'll call intermittency. And a good portion of my talk will be explaining exactly what this means. In a rough sense, this means membership in certain function classes. And the picture of an intermittent function is a function which has spikes and deviations away from sort of the average behavior. All right, so just a few comments on this theorem. The dissipativity and the intermittency are in accordance with what we observe about turbulent flows. All right, so that's really sort of the driving force behind why one should care about these solutions. And one nice consequence of this theorem is that we're able to reformulate, in a sense, and reprove a classical conjecture from hydrodynamics due to Onsager. This is the well-known Onsager conjecture. And as given that we provide, in a sense, a new proof of this conjecture in the intermittent setting, we call this the intermittent Onsager theorem. All right, so in the rest of my talk, I want to tell you a little bit about turbulence, specifically dissipativity and intermittency. And then I want to tell you a little bit about the math that goes into the construction of these solutions. All right, so let's start with the turbulence backstory. All right, so I have written here again the non-dimensionalized Navier-Stokes equations. The non-dimensional parameter is this Reynolds number, which I can compute if I know the characteristic velocity and length scales in my fluid, and also the kinematic viscosity coefficient nu. And I'll use interchangeably Reynolds number and nu. Reynolds number going to infinity means nu, in a sense, is going to 0, and that's the case of the Euler equations that I'm most interested in today. All right, so let's look at a few pictures of different kinds of fluids so that we have an idea of what's happening with turbulence. All right, so what's pictured here is a fluid in the exterior of a cylinder. So here's the cylinder, and the fluid is moving in a nice sort of organized pattern, very clear streamlines. There's a sort of continuous in time symmetry associated with the solution, and it's absolutely not turbulent. And that's because the Reynolds number is not big enough. In order to see turbulence, we have to start increasing the Reynolds number. And on the way to turbulence, as the Reynolds number increases, lots of interesting dynamics occurs. So this is a picture of a von Karman vortex street. And what's happening is that the cylinder is now over here, and the fluid is being forced past the cylinder. And the continuous in time symmetry is broken in the sense that you see these vortices shedding in an alternating top and bottom fashion. All right, so this is a very beautiful picture, but it's still not turbulent. In order to see turbulence, we have to increase the Reynolds number by another order of magnitude. And so this is a picture of what could be called homogeneous isotropic turbulence. And it's homogeneous in the sense that it's translation invariant in space. And it's isotropic in the sense that if I zoom into small scales, the sort of large scale left to right motion of the fluid is forgotten, and I just see isotropy at the small scales. All right, so this is homogeneous isotropic turbulence. And it arises at large Reynolds numbers. And what I want to tell you a bit about now is properties that we can observe about these turbulent flows. And the properties that I'm specifically interested in are the energy dissipation and the lack of smoothness in these flows. All right, so I have here a picture, if you will, of the Kolmogorov-Onsager sort of idealization of turbulence. And so there's a few ingredients. The first is a symmetry assumption. These are the isotropy and homogeneity that I already mentioned. But there's also a self-similarity assumption in the sense that these eddies that you see are reproduced sort of exactly at sequences of finer and finer scales. All right, and one of the other key ingredients of this picture is dissipativity. So of course, if I have a very viscous fluid, you can imagine a vat of oil or something. If I stir it around, the viscosity will bring the fluid to rest. But the dissipativity assumption that I'm working with here is that it's in fact not just the viscosity which dissipates energy, but this cascade of energy down to smaller and smaller scales. And the idea is that this energy is in a sense lost at infinite frequency where it's dissipated into heat. And as I'll detail a bit later, there's a sort of model function that one should think about when considering these turbulent flows. And it's the sum of sine waves. And I've weighted this sum of sine waves by the minus cube root of the frequency. And that's the first occurrence of the 1/3 fraction in this talk, and it will absolutely not be the last. All right, so let me say a few more specific things about dissipativity and intermittency. So let's start with dissipativity. So if I take a solution of Navier-Stokes, depends on the value of nu, I can calculate the energy dissipation rate. So if you will, the energy dissipation rate for a particular solution is, let's say, 1/2 ddt of u L2 norm squared. And I expect this quantity to be negative if my solution is dissipative. And if I rearrange the equality, the energy balance, I find that the energy dissipation rate depends, first of all, on the viscosity coefficient nu, but also appearing is this Duchon-Robert measure. And what the Duchon-Robert measures is the contribution of the nonlinearity to the dissipation of energy. And why should this be contributing at all? Well, it's because in order to derive the energy balance, I should take the dot product with U nu and integrate by parts. But U nu is not necessarily smooth. So I have to mollify it before I can do this integration by parts. And this is the mollifier appearing in this integral. And the nonlinearity is quadratic. And so when I multiply by U, I get something which is cubic in the velocity. And so this Duchon-Robert measure basically quantifies whether or not integration by parts is functioning correctly in the nonlinear term. All right, and the zeroth law of turbulence says that if I compute this energy dissipation rate as a function of nu, and I send, that should be nu to 0, and I send nu to 0, then I get a strictly positive number epsilon in the limit. And this is the zeroth law of turbulence, not because we have a proof, but because it's observed so consistently in experiments and simulations. And I should say that not only do we not have a proof, we don't even have a single example of a sequence of solutions for which you can compute the energy dissipation rate and show that these solutions converge to a dissipative solution of Euler. So there's a long way to go in terms of mathematically validating the zeroth law. All right, so at this point, it's appropriate to mention Onsager, who really understood something fundamental about the zeroth law. And what he said was that turbulent dissipation could take place just as readily without the final assistance by viscosity. And this is because the standard proof of the conservation of energy does not apply because the velocity field does not remain differentiable. So Onsager really put his finger on the culprit behind this anomalous dissipation of energy. And he went on to conjecture exactly how much differentiability should be required in order for weak solutions to conserve the energy. And his conjecture is stated in the scale of Holder continuous functions. And the threshold, if you will, between dissipativity and conservation is 1/3 Holder continuity. And it is absolutely not an accident that the model function that I showed you for these turbulent flows had that 1/3 fraction of the frequency in front of it. All right, so this is Onsager's conjecture, made more than 70 years ago. And let me say a little bit now about where the 1/3 comes from. All right, so if I'm making measurements of turbulent fluids, one natural measurement to make is to take a velocity increment centered at some point x and in the direction z, and then integrate this quantity raised to the pth power over the torus. And what Kolmogorov posited in his phenomenological theory of turbulence is that these integrated or averaged velocity increments obey a sort of scaling law. And that scaling law is phrased in terms of the energy dissipation rate, epsilon, and the size of the velocity increment z. And if I simply assume that some scaling law of this type is obeyed by these average velocity increments, I can use dimensional analysis to determine what the powers on these quantities are, right? Because epsilon has some units, z is a length scale, and in order for the units to balance with the left-hand side, it turns out that the single acceptable choice of these exponents is p on 3. So I expect these velocity increments to scale like epsilon mod z to the p on 3. All right, let's parse this in terms of math though. If I want to measure the b 1/3 p infinity norm of my function, what I do is I take a velocity increment centered at x in direction z. I integrate over all points x after raising it to the pth power, and then I weight it by some power, some fractional power of z. And if I simply rearrange this equality by putting this on the other side, I'm measuring exactly a Besov norm of 1/3 regularity in LP, and I'm saying that it's finite, and it spits out this number epsilon to the p on 3. All right, so in terms of regularity, Kolmogorov and Onsager are saying that turbulent solutions of these equations have precisely 1/3 of a derivative in LP for all p. And an example of a function which satisfies that kind of estimate is exactly this sum of sine waves. All right. So that's the sort of Onsager-Kolmogorov story. And some remarkable progress has been made towards validating that at the mathematical level. So the first half of the Onsager theorem should be a rigidity theorem, which says that under appropriate assumptions, the energy is conserved. And the appropriate assumption is that the solution has essentially 1/3 of a derivative in L3. That's what this Besov space is. And that should be L3 integrable in T. And if I have that much regularity, then energy is conserved. And let's just see in a rough sense where that threshold comes from. So if I look at this integrand, I want to show that it's 0. Notice that this integrand is cubic in the velocity v, and there's one differential operator. And so if I just take one differential operator and 3 copies of u, this is going to be well defined if each copy of u can afford 1/3 of a derivative. And furthermore, it should be measured in L3 because this quantity is trilinear. All right, so that's the theorem of Constantine-Ern TT. All right, the flip side of this theorem should be a flexibility theorem, which says that below this regularity threshold, energy may in fact dissipate. And this is what was proved by first Isett in the context of non-conservative solutions, and then shortly thereafter by Buckmaster, Deuelis, Shekeli, and Vicol in the context of dissipative solutions. And the solutions constructed by these groups belong to C alpha Tx for alpha less than 1/3. But they have no regularity in any LP space above the 1/3 threshold. All right, so I guess to sum this up, we can call the Onsager theorem the combination of these two results. And one should notice that there's a mismatch between the flexibility and the rigidity statements. Namely, the flexibility statement is formulated in C alpha, and the rigidity statement is formulated in an L3-based Besov space. All right, so we've seen the Kolmogorov-Onsager picture, and we have some idea of what's happening at the mathematical level. But let's go back to the physics, the experiments, and the simulations in order to figure out whether or not this picture is really correct. And what I'm interested in assessing is this regularity exponent, right? So this picture is the regularity exponent as a function of p. And what Kolmogorov says is that it's exactly 1/3 for all p. All right, so what's observed in experiments and simulations? So I have a lot of text on this slide, and that's because there's a lot of people that are thinking about this question, and they consistently find that there's some deviations from the Kolmogorov predictions. And these deviations take the following form. So at the p = 3 level, we see exactly 1/3 of a derivative in L3. And when p is not equal to 3, we see deviations in the downward direction if p is larger than 3, and in the upward direction if p is less than 3. And to give you an idea of sort of who's been thinking about this, so Onsager and Kolmogorov themselves were aware of the idea that their predictions may have to be adjusted. And even to this day, people are trying to understand whether or not K41 is accurate. And in a sense, you could sum up their findings with the following statement. This B1/3 3 infinity space is really the correct space for turbulence. All right, so these solutions should exactly have 1/3 of the derivative in L3. But if I leave the L3 based regularity scale, then 1/3 is not the correct threshold. All right, so what's the culprit behind these deviations from Kolmogorov's predictions? The culprit is exactly this concept of intermittency, which you should think of as synonymous with sparsity. And what sparsity does is it breaks the self-similarity assumption. So instead of seeing the whole screen filled up with eddies, what you see are a small number of eddies of increased intensity. And that's sort of the characteristic feature of an intermittent function, if you will. All right, so what kind of function has this intermittent property, if you will? So a classical example would be the Cantor function or the Heaviside function. The Cantor function, you can compute what the various exponents could be. I forget what they are off the top of my head, but in any case, they depend on P. In the case of the Heaviside function, this function belongs exactly to B1/P infinity. And I picked this function because if I were working in the context of compressible fluids, I would see shocks, which are simply these jumps, and shocks have exactly this regularity. All right, so it's intermittency, or this sort of large deviations from the average behavior, which are the culprit behind these anonymous scaling exponents. And this then is really the motivation for the theorem that we proved. I want to build solutions which exhibit the deviations observed in experiments and simulations from Kolmogorov's theory. So I want my solutions to be intermittent in the sense that they belong to the right L3 space, that's B1/3 3 infinity, but they exhibit anomalous scaling at the L2 level. So B alpha 2 infinity for alpha bigger than 1/3. And I, of course, want these solutions to be dissipative in order that I respect the Zeroth law. And this is exactly what we proved. So you can give me any exponent in between 1/3 and 1/2, and I can give you a solution which belongs to H beta in space, continuously in time. And it furthermore belongs to L1/1 minus 2 beta, which goes to infinity as beta goes to 1/2 from below. All right, so these solutions live almost in H1/2 and almost in L infinity. And if you interpolate between H1/2 and L infinity, you get B1/3 3 infinity, which is exactly the right space. And that's why we call this an intermittent Onsager theorem. It's because it reaches the Onsager threshold, but in the appropriate L3 based Besov space. And the intermittent Onsager theorem that I proved recently with Vlad was based on, as I said, an earlier work with Tristan, Nader, and Vlad. And in that paper, we were able to reach the H1/2 threshold, but not the L infinity threshold. All right, so in the remaining 20 minutes or so, let me say a little bit about the construction. All right, so you recall that my model function for turbulence was some weighted sum of sine waves. And the inspiration for my construction will be a weighted sum of some type of wave, but sine waves are not appropriate. I should have something which is intermittent, meaning roughly that it has this sort of sparsity built into it. And what I'm going to do is reverse engineer a solution of the Euler equations by building this series term by term. All right, so let me say something about what my fundamental building block WK is. So it's what's known as a Mikado flow. You should picture this as just an inviscid straight pipe flow. So I pick some vector direction. I take a periodized line in the torus in that vector direction, and I concentrate around that periodized line, fluid flowing parallel to the line. And so what is depicted here is a cross section. And so the fluid flow is supported in these little circles. These are cross sections of the pipe, if you will. And the sparsity is quantified by the gap between the thickness of the pipe and the distance between neighboring pipes. And I'll use lambda with some subscript in order to quantify the thickness. And SK is my sparsity parameter, and it's in between 0 and 1. And it tells me the ratio between the thickness of the pipe and the distance between neighboring pipes. All right, so this is my object. It's a stationary solution of Euler, and I want to build some infinite superposition of these objects, which in the limit is a weak solution of Euler. All right, and this intermittent function has both pros and cons. So the pros are that the various LP norms scale very differently because of the sparsity. And the second pro is that all this empty space gives me a lot of freedom into where I put my actual pipe. I could put it somewhere else in this periodic cell, and that would be totally acceptable. All right, but of course, this intermittent object comes with its downsides as well. So one downside is, again, the different scaling of the LP norms. And the reason is that I have to make fairly precise estimates on my solution in order to get H1/2 regularity. And these estimates depend quite delicately on whether or not I'm in the support of the pipe or whether or not I'm in the empty space. So I need my estimates to be localized so that they respect this sparsity. All right, so my infinite sequence of approximate Reynolds system. Euler Reynolds system says that I have an approximate solution UQ, and it's only an approximate solution because I have the divergence of the Reynolds stress RQ on approximate solutions where UQ converge in H1/2 intersect L infinity. I'll need that in order to deduce the correct regularity on my final solution. And I also want RQ to converge to 0. And if you look at the structure of the Euler-Reynolds system, this is inside a divergence, this is inside a divergence, this is quadratic, this is linear. And so H1/2 at the level of U corresponds to W11 at the level of R. And similarly, L infinity at the level of U corresponds to L infinity at the level of R. So I need convergence in these topologies of the Reynolds stress R. All right, and what's sort of the picture for how I build this solution? The picture is that I'm filling out the frequency shells Q by Q. So my frequencies are indexed by lambda Q. And as lambda Q goes to infinity, I'm inserting higher and higher frequencies into my solution. And I do that using an ansatz. And what my ansatz says is that if I take, if I want to obtain my next iterate UQ plus 1, I should start with my previous iterate which oscillates at the low frequencies. And then I should add to it something high frequency. This is my pipe flow times a measurement of the error. And we'll see why this 1/2 normalization is the correct normalization in front of this high frequency object. All right, so let me just remind you again what my pipe flow looks like. So again, this is a cross section of my torus. There's periodic cells, and inside each periodic cell, I see one little segment of pipe, which is very sparse compared to the size of the periodic cell. And that sparsity parameter is S, and lambda is the thickness of the pipe. All right, so the sparsity parameter quantifies a few things. First of which is the measure of the support of this object. So this is SQ squared. And then it also quantifies the number of choices that I have for the placement of this pipe inside this cell. And that's SQ to the -2. And I furthermore have derivative estimates and LP estimates, which say that the LP norms depend on the sparsity parameter. So if I plug in P equals 2, I get 1, because 2 over P minus 1 equals 0. If I plug in P equals 1, I get SQ, which is much less than 1. And if I plug in P equals infinity, I get SQ inverse, which is much larger than 1. All right, so the intermittency is baked into this building block, if you will. All right, so let's unpack this construction a little bit. And in order to unpack this construction, let me consider a simple example in which the Reynolds stress, which was supposed to be a symmetric matrix, only has something in the top left component. So I can write it as E1 tensor E1 times some scalar function R. In that case, my ansatz is very simple. It's the difference between velocities, UQ plus 1 and UQ, is exactly the square root of minus the Reynolds stress times a pipe which points in the E1 direction. E1, of course, because my Reynolds stress only lives in the E1 tensor E1 component. All right, so I have my ansatz. I should plug it into the Euler-Reynolds system and see what the leftovers are. And what I get is the following. So the new velocity field satisfies a new equation where the leftovers are given by the oscillation error, the transport error, and the Nash error. All right. So first, let me comment on why I normalize this W in L2. And it's because of the scaling of the nonlinearity, namely that it's quadratic. So what I would like is for WQ plus 1, my velocity increment, to help me get rid of RQ. And if I plug in my ansatz in this setting, I get that this is exactly equal to RQ minus RQ times W tensor W, at least the first component. And I simply factor out RQ. So this is something low frequency. This is something with 0 mean if W is normalized in L2, which makes it high frequency. And that's why I normalize things in L2. All right, so I have all these various leftover terms, transport, Nash, and then here's what's left over in the oscillation error. I have to put these in divergence form. So I have to write them as the divergence of a new stress, and then I have to estimate them. And the success of my scheme depends on the accuracy of my estimates, basically. All right, so let me say at the level of a bird's eye view, what sort of we're aiming at here. We're aiming at convergence in H1/2 intersect L infinity. And what I want to tell you about is what intermittency has to do with these function spaces. All right, so there's a few main issues, and this is what I'll focus on in the remainder of the talk. The first is the linear error terms. So these are the Nash and transport errors. they're linear in the velocity increment WQ plus 1. And it turns out that these linear error terms tell me exactly how much sparsity is appropriate. And then the second issue is somewhat technical in nature. And this is where we rely quite a bit on some heavy but very useful machinery that was developed in the first paper with Tristan, Nader, and Vlad. And then finally, I want to tell you a little bit about nonlinear interactions between different pipes and how sparsity figures into that picture. All right, so let's start with the linear error terms. So the simplest linear error term is the Nash error, and it's WQ plus 1 dot nabla UQ. And I should write this in divergence form. So that means I should essentially apply an inverse divergence operator to this product, and I'll get some new Reynolds stress. And when I estimate that new Reynolds stress, I have to estimate it in L1 and L infinity. And when I estimate it in L1, I'll be able to appeal to the L1 norm of this building block W, which was my pipe flow. And that L1 norm spat out a positive power of my sparsity parameter. And so if my function is very sparse, if my pipes are very sparse, then this L1 estimate is happy because I get to appeal to this small parameter SQ. Unfortunately, I also have to estimate this in L infinity, which means I have to pay the L infinity norm of this object. And this is given by SQ to the -1, which is very large if my pipes are very sparse. And so I have to balance the sparsity constraints from both the L1 perspective and the L infinity perspective. And if I decorated this calculation with a few more parameters, it would take me probably 5 minutes. You would find that there's a single choice of SQ which balances these two constraints. And what this means is that even at the linear level, I'm completely constrained in how much sparsity to use. And I don't know how to derive this number from, let's say, any physical argument, but it's clear at the level of the estimates that it's the only choice. And in order for my scheme to close, I have to make sure that this, this intermittency parameter choice works in all the other error estimates. And it's a bit of a miracle that it does. This was not obvious at all to us when we at least wrote the first paper. All right, so I have a choice of sparsity parameter that came from the linear errors. Now let me say something about estimating derivatives. All right, so I have to estimate spatial derivatives in order to get H1/2 regularity. And I have to estimate many spatial derivatives. And this is because, as is characteristic of a Nash iteration, I lose derivatives along the way, and overcoming that loss of derivatives means propagating many spatial derivatives. But because Euler has a natural sort of transport structure, I need not only spatial derivatives, but material derivatives. And what sort of estimates do I have to make? Well, a good way to think about it is consider any differential operator which can be amalgamated using combinations of these various differential operators in any arbitrary order. I have to apply this new operator to, let's say, my velocity increment and estimate the result. So combinatorially, that's already quite difficult. But even worse, the sparsity makes these estimates very delicate on the location in space. And so we need to localize these estimates. And what we essentially use in order to achieve this localization is an ad hoc wavelet decomposition, if you will, of our solution. And what this wavelet decomposition does is it tells me what the frequency is in the spatial variable. it tells me what the frequency is in the Lagrangian variable for the material derivatives, and it knows everything about position and amplitude. All right, so at a technical level, this contributes greatly to the length of the first paper. All right, so let me close by saying a few things about one of the nonlinear error terms. All right, so I gave you an ansatz, which said that my velocity increment was equal to the square root of the stress, roughly speaking, times this pipe W. And I have a sparsity parameter, which is the good one. And you should be asking, why are these pipes colliding at all? They're all stationary. Well, what happens is that in order to respect the transport structure of Euler, I have to let these pipes deform with the velocity field UQ so that the material derivative vanishes. And when I let these pipes deform, they may become very twisted, at which point I have to cut them off and start with a new set of straight pipes. And the picture you should have in mind is that I have many regions of time, which I patch together using a partition of unity. And in each one of these regions, I have a dedicated set of pipe flows. Now, if I flow two of these regions toward each other, these pipes could collide in the middle because they're moving and twisting and deforming. And I have to prevent those collisions. All right, and this is where sparsity comes in to save the day. So at this point, it's really a geometric argument. It has nothing to do with sort of convex integration writ large. And what's the picture? So I have some small spatial scale, which is the characteristic length scale of my stress. And so I should zoom into that scale and look at the pipes that are living on one of these little cells. They're twisted and deformed. And I need to find enough room for a new set of straight pipes. And as you can imagine, sparsity aids in this process quite a bit. So what do? The first thing is I place these pipes one at a time. So I zoom in on a single anisotropic rectangular prism, which is going to eventually hold a single pipe. And I focus my efforts just on this single prism, and then I'll do all the prisms one by one. All right, now, if you're a pipe, if you're the blue pipe, and you're staring into this rectangular prism, the picture that you see is a square, which is inhabited by obstacles. And these are the old pipes, these obstacles. All right, so I project the whole picture down onto the front face of the prism, which is perpendicular to the pipe. And at this point, I simply apply a covering argument, which says that inside this square, I have to find some empty space for a new pipe. And I can simply cover the twisted, deformed pipes by little grid squares. And I can count how many grid squares are occupied by these pipes. And if you do this accounting, you can see exactly how much sparsity is needed in order to ensure that there's empty space for the new pipe. And miraculously, you get exactly the same good sparsity parameter that we got from the linear error estimates. All right, so let me just say then, in closing, a few possible further directions for this research. So I think ground zero would be an understanding and further optimization of our construction. So one thing that you could hope to understand would be the structure of the singular set of my solution, or maybe even more interesting would be the Duchamp-Robert measure where the dissipation is happening. And you'll notice also that I said something about the regularity exponent in L2 and L infinity, and then by interpolation, everything in between. But we were not able to prove anything in this range. And I'm not even sure what to expect there. All right, a different direction would be to take some property of turbulent fluids, as we did in this talk, and then build solutions which match or do not match this property. I think a few natural choices would be helicity, which is another formal invariant of the Euler equations. Or you could try and build solutions which satisfy the local energy inequality. And then finally, I think it'd be quite interesting to use this technology to solve other Onsager conjectures. There's many fluid equations, each of which has their own Onsager conjecture. And the only one which is currently closed is 3D Euler. And of course, one could attempt to use these techniques in the context of some other nonlinear PDE. I think maybe a kinetic or dispersive equation would be a natural choice. All right, let me close there and thank you for your attention.
Okay, so any question for Matt?
Sure, I got a question.
Yeah, please.
So maybe I missed it, but what does the energy profile look like for your examples?
So I can if you give me a smooth energy profile, could be decreasing, could be increasing, could be doing any crazy thing, I can build a solution with that energy profile.
Okay, so it doesn't, so decreasing sort of is, I mean, you can really make it do anything.
The thing is that Euler is reversible, right? So if you tell me you've built energy decreasing solutions, I just turn time around and I give you an increasing one. In order to pick out the energy decreasing property, I have to remember that I came as an inviscid limit of Navier-Stokes.
Mm-hmm.
That's where the decreasing energy will come in. And at this point, the constructions are not sophisticated enough to pass through the inviscid limit. But I think that would be a really good goal.
Okay, thanks.
Any other questions? So Matt, is the construction really can push to 1/2 or infinity? You can, right? Can you push the like exactly 1/2?
Can you get
1/2?
exactly to 1/2? I think that's extreme. That would be extremely difficult, and I'm actually not sure that you can expect such a theorem to be true. If you consider the space B1/3 3 infinity, so this is sort of the exact threshold in L3.
Right.
Shocks dissipate energy, but vortex sheets conserve energy, and they both live in exactly this function space. So I actually don't think that there's sort of any general theorem that can apply to a wide class of solutions, because what's going to be happening is probably predicated quite delicately on the actual properties of the solution that you're looking at.
I see. Yeah. Any other question for Matt?
Sure, one more. So you mentioned an open question about what the singular set looks like. What do you know?
We didn't include this computation in the paper, but what I think you could show is that there's some set S which has Hausdorff dimension 2, so 2-dimensional Hausdorff measure, which is non-zero, and outside of that set, the solution is smooth.
Okay.
But that set, I think, is quite rough. It's probably actually dense.
Okay.
In order to build a solution with a more interesting singular set, it would take a bit of work.
Okay, thanks.
So do you think the singular set can be an object dimension? I mean,
Say again?
dimension. Do you think the singular set can be arbitrary dimension, like between 0 and 3?
So
you mentioned like a 2-dimension, right? You just said 2
yeah,
dimension.
so I think the H1/2 L infinity regularity essentially dictates the Hausdorff dimension of the singular set. And
Sure.
actually, this is something that in the physics and fluids communities, people try and estimate. And I think they've gotten like, that the dimension of the bad set should be 2.7 or something.
I
But
see.
yeah, I mean, this is very fine information, which is sort of beyond the scope of reasonable measurements and experiments.
Any more questions for Matt? If no further questions, let's thank Matt for a beautiful talk. Yeah. So yeah, I guess maybe is there still like a talk